Good afternoon, and thank you for joining today's webinar from Spec Innovations, Building a Digital Thread. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I'd like to go over some housekeeping. During the presentation, feel free to send us questions to marketing@specinnovations.com, and we will get back to you with an answer as soon as possible. You can also interact with us on LinkedIn through the InnoSlate users group or through Twitter using the handle @SpecInnovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Now I would like to introduce to you our presenter, Andy Tapia, Spec Innovations Systems Engineer. Andy has been one of our main systems engineers for more than 3 years and is an alumni of the George Mason University Systems Engineering School. In today's webinar, Andy will discuss building digital threads using integrated program management, systems engineering, and design engineering tools. These tools support the entire product lifecycle. He will also discuss when to integrate and when to curate the digital products of these tools. Feel free to send him any questions through the LinkedIn users group or send him an email to andy.tapia@specinnovations.com. Now I'll hand over the controls to Andy and we'll get started.
All right. Hello, and thanks for everyone coming out for this webinar, Building a Digital Thread. My name is Andy Tapia, and I am a system engineer here at Spec Innovations, where my colleagues and I have developed Specter, a lunar rover that serves as a testament to InnoSlate's ability to help users build a digital thread. And to show you how we did it, first I'm going to provide a little more information about our company and how we see the digital thread, and then explain how we came across the idea to build Specter, which all started with NASA's Break the Ice Challenge. Then I'll walk through how we demonstrated InnoSlate's digital thread with Specter, starting from when we initiated the project and all the steps taken to its final construction and demonstration. So we are the developers of InnoSlate, a cloud-based MBSE tool designed to support the system engineering lifecycle from start to end, or concept to disposal. And we are always trying to release user-driven updates to our tool. We do our best to listen to user feedback and trying new things to support the system engineer. Currently, we're on version 4.7, which was released earlier this year. That was targeted more for user experience and enhancements, but we did add something new, such as compilation view, and I believe that would be in our help center, not reviewed today, but feel free to look there. And so our story begins when we first heard about NASA's Break the Ice Challenge in the summer of 2021. And we were too late to submit the proposal at the time, but we thought it'd be a perfect way to demonstrate InnoSlate's ability to support the digital thread. And so to do this, we set a goal to create a Lunar Rover prototype system using a complete digital thread, and therefore limited the scope to the physical boundaries of the Lunar Rover. So I've been throwing around the term digital thread a lot, and a lot of you may have also heard it many times. But for the uninitiated, I'll go ahead and explain what I think it is. And so what we have here is, according to the most recent 5th edition of Incozi's System Engineering Handbook, a digital thread is a set of interconnected, cross-discipline model data that seamlessly expedite the controlled interplay of digital artifacts to inform decision makers throughout a system's lifecycle. So in other words, or in my words, I would say, digital thread is essentially a digital record of all the engineering data used to drive engineering decisions throughout the system's lifecycle. And I would say this includes diagrams, models, documents, spreadsheets, PDFs, and more that can take the input and effort of multiple engineering disciplines, and maybe not even engineering disciplines. And ideally, they'd be archived or stored in one knowledge database to make it easier to find during a project or after a project's completed for reuse. So NASA's Break the Ice Challenge, I mentioned it before. It was a multi-phase competition hosted by NASA intended to help create innovations and new technologies that could help support lunar missions and a sustained human presence on the moon in the near future. It's kind of like what they're doing with the Artemis missions right now. In 2021, beginning in 2021, they had phase one, which is what we addressed. And I believe currently right now it is in phase two, which is more geared towards furthering the prototype architectures that were developed in phase one or for the winners of. And so inside the challenge, NASA was searching for solution architectures that can excavate lunar regolith, which is a fine lunar dust that covers the surface layer of the moon, that can also maximize water delivered to a designated site location, minimize the massive equipment needed for the mission, and also minimize power consumption of the systems used in the mission. The ultimate goal was to develop an architecture that could feasibly extract 10,000 kilograms of water from lunar regolith in 365 Earth days. And extracting this much water is necessary not only to support human life, but as is aligned with the goals of the Artemis missions, they also would like to potentially support extended missions to Mars and beyond, as the water could be converted into rocket fuel. This kind of would turn the moon into kind of a celestial pit stop for humanity. It's a very noble goal. Okay. So before I start walking through about how we address the challenge using the digital thread, I wanted to align it with the famous system engineering V model that we have right here. What you see here on the left-hand version, on the left-hand side, is the V model, our version of the V model, beginning with the design and analysis leg, into the integration and verification leg, while the program management parts are ever present throughout the whole process. And so in order to support the digital thread, we've designed InnoSlate's features to meet each part of the V model, shown on the right-hand side using Documents and Diagrams view, which includes a CAD viewer, modeling and simulation, project management view, test center, and different tool integrations like GitHub, ANSYS, SDK, and MATLAB. Using our best practices and engineering rigor, we took on the challenge and used our tools end-to-end digital thread capabilities to help solve this problem. Okay, so to start, to initialize our Lunar Rover project, we use the documents, diagrams, and project management views within InnoSlate in the program management process. In the V model, in the system engineering V model, this would be the ongoing and parallel management work that occurs throughout the system's lifecycle. And next we created a project management plan, or the PMP, to start the Lunar Rover project as a document in our InnoSlate database. And this helped define our project scope, technical execution, schedule, and budget. And as it is a living document that is meant to be continuously updated over time, this was kept in our database for us to revise or refer to at any time, at any point in the project. Next, we had a statement of work, or an SOW, that defined more in depth the technical execution of the Lunar Rover project. We broke down the project into four main tasks to help produce the Lunar Rover prototype. And these tasks would include the research and design phase, build phase, test phase, and demonstration phase, which are all shown in the action diagram on the right-hand side. We did have a fifth task that was mainly used to help us keep track of the challenge deliverables that needed to be met for phase one's criteria. But since we entered rather late and didn't go into it, we use them more as guidelines to help develop the Lunar Rover prototype even further. Sorry, water. Okay, And you'll notice that each task on the diagram on the right has input and output entities that result. And those entities would be either technical documents or products for the project. So next we had schedule. Yeah. So from the statement of work action diagram, we were able to automatically generate a schedule by selecting a new diagram view from a drop-down list. And that can be either a timeline diagram or a Gantt chart if you execute the action diagram. So with the timeline diagram on the left, that was the diagram mainly used throughout the project to track the progress of SOW tasks and subtasks and to help us maintain awareness of project deadlines and milestones. The Gantt chart on the right, as I mentioned before, is created by executing the SOW action diagram. And using that information, we created additional dependency entities using the IOs there to create those dependency relationships and connect the different SOW tasks and subtasks. You can see the dependencies as the black arrows, and they show the start and finish of the tasks to create a more accurate critical path inside the action diagram simulations. So next we had the Kanban board, which was also used to help us keep track of the progress of the different tasks. But however, in our Lunar Rover project, we mainly relied on the timeline diagram to stay on top of tasks. So we used the Kanban board just a little differently. And one of the ways we used it differently was to keep like a live to-do list for some of the lower level work items that's usually assigned to a team member for timely completion. And to create the Kanban board, we used a project workflow template and modified it as we needed to. But the default way it shows up as a template is having a to-do list, a in progress list, and a in review list. And I believe there's a completion list too. So with task one, the research and design phase, uh, to complete that, we use InnoSlate's documents and diagrams views, as well as the modeling and simulation and the CAD viewer. In the system engineering V model, you could say this work took place during the architecture development and systems design phases. So for task one statement of work, we broke that down even further into three subtasks, research design and incorporating InnoSlate's digital thread. And from this task, we developed a set of requirements, bill of materials, and a final report, all stored within InnoSlate's database. And so from here, after getting project planning out of the way, we proceeded to conduct a research to help us determine a system architecture. And at the beginning of our research, we looked at NASA's Break the Ice Challenge rules and the documentation to extract more information such as the mission requirements, which is all recorded in our requirements documents feature. These are things such as excavating icy regolith at the excavation site, extracting water from the icy regolith using the NASA water extraction plant, delivering water to the delivery site. And as we're making these requirements, there is a quality checker. You can see shown as the 75% in green that ensures that the requirements you write are written in a way that's consistent with good requirements standards. I believe it's based on Nkozi's guide to writing requirements, to make sure that they're singular, they're complete, they're ambiguous, and there's even more than that included. And beyond that, we also gathered some domain information about the lunar environment, specifics about the regolith and the environment there, some additional NASA assets we could rely on, performance parameters, and environmental constraints. Okay. And so next we had a context analysis, which was conducted after gathering the information and the requirements. This is an as-is system architecture that was produced within an asset diagram by defining the existing equipment and systems that are external to the Lunar Rover system produced from the Lunar Rover project, which include ground communication on the Earth that will send telemetry and collect the data as it needs to from the rover during the mission on the Moon, the lunar lander, or rocket that will transport the rover from the Earth to the Moon to its initial landing site. And then we have an excavation site and a delivery site that's been designated for us. And these are locations where where there's ideal concentrations of regolith, of icy regolith, to be found, and where water will need to be delivered for humanity. And as well, we have some NASA assets, a water extraction plant and an optional power plant that can be provided by NASA to convert the excavated regolith into water and provide power to the rover. See, I forgot those there. Okay. And from that context analysis, we created a concept of operations document to define the initial Lunar Rover system design. And we used that to help brainstorm and help define the initial rover system design. That was created in Documents View, kept in the database as a concept of operations document type. And we used a NASA Defense Acquisition template for that. And once we had that rough ConOps that was designed and documented, we had a functional analysis. And we conducted that to enable the creation of functional requirements for the rover prototype system. And we made two diagrams inside of InnoSlate to assist that process: the hierarchy of functional elements and the mission scenario action diagram that you see below on the screen. And the mission scenario visualizes the Lunar Rover's mission and steps through in order the execution of all the actions that the rover will need to perform on its mission. It's a little hard to see, but basically, once the Lunar Rover lands via the lunar lander, the rover is going to start heading to the excavation site, where it'll start the process of excavating and delivering regolith and water, regolith to the NASA water extraction plant. And then after the NASA water extraction plant has extracted enough water, the rover will switch modes and start the process of delivering water from the plant to the delivery site. And during the processes, the rover is going to maintain its battery levels, perform recharge cycles, and as well as exchange data and communicate with the Earth as it needs to. So we wanted to build the Lunar Rover within a summer time frame, ideally, and so to speed up the process of building it, we compared some commercial and open source rover products that could help us. While we were looking across these products, the main things we were looking out for were cost, functionality, and the time to assemble, which gives us time or allows us to focus on innovating only where we needed to, such as in technical gaps like the excavation mechanism. In order to select the best design for the prototype as well, we used a functional requirements checklist comparison shown on the right-hand side, and ultimately used a hierarchy or analytical hierarchy process methodology, AHP method, to help us choose. So using the checklist and the AHP methodology, we selected the Leo rover to be used for the Lunar Rover project. It fit the bill for most of the functionality. And speaking of bills, we created a bill of materials, or a BOM, that helps us record the equipment, tools, and additional materials here and there that needed to be purchased to start beginning the process of building the Lunar Rover prototype. We also made an asset diagram that was created to track the additional details, such as tracking the order numbers, tracking numbers and order numbers for components. So from that, we built the cost breakdown structure, or the CBS, that was created using that hierarchy chart to record the costs incurred by the Lunar Rover project, including the materials inside the BOM. The tools, everything, the tools, equipment, the additional materials, they're decomposed in the hardware cost entity inside the CVS. And to estimate the total cost, all we needed to do was to go to that top entity hardware, roll it up inside of entity view, and see what the cost was by adding all the attributes there. So ultimately, we landed on the final prototype design for a Specs Lunar Rover project, which combines the Leo Rover prototype with the excavation subsystem, the storage subsystem, and some additional navigational equipment such as LED headlights and a LiDAR sensor. ANSYS's CAD tool and space claim helped support our need to modify the Leo rover design, and it helped us design some of the 3D printing files for components such as the excavation claws, the storage unit, and the tire fenders shown in task 2, upcoming. The InnoSlate's CAD viewer was then used to store the CAD designs of the final Lunar Rover prototype by uploading the file as an artifact entity, which can display CAD designs, and you can see that on the right-hand side there. It's a static image, but you're able to move around and it spins around for you too when you have the viewer open. There it is. Yeah. And so now we have from the as-is system architecture, it's been updated with our Lunar Rover system asset, completing it to be the 2B system architecture. And so the Lunar Rover is going to connect all the external systems together to enable regolith excavation and the water extraction processes on the moon. Oops. There you go. And using the site locations provided by NASA, we could map a travel route for the rover to follow during its mission on the moon. And we know the rover will follow a path from the excavation site to the water extraction plant to the delivery site over the course of the mission. And the distances between the sites are meant for a full-size rover, but for the purposes of our project, and for testing, we scaled the distances a little bit down for the rover prototype, which had some basis on the Apollo Lunar Rover. Okay. Next, we had an excavation scenario that was created inside of an action diagram to model the excavation process the rover is going to follow each time it navigates to the excavation site on the lunar surface. Then we performed the simulations using the model to estimate regolith excavation capacities per cycle and across the mission. Let's see. And then we have task 2, the build. And to complete task 2, we used InnoSlate's modeling and simulation tool and tool integrations, ANSYS, SDK, MATLAB, and GitHub to help us complete it. Inside of the system engineering V model, we would say this work took place during the hardware and software acquisition phases. Okay. We also broke down task 2 using an SOW into 3 subtasks: building the 3D printer, printing the additional equipment, assembling the Lunar Rover prototype, and incorporating InnoSlate's digital thread. From this task, we produced a final report for task 2, as well as the Specter Lunar Rover prototype. So from there, we had a Creality Ender 3D printer that was purchased for 3D printing and printing the additional materials needed for the construction of the Lunar Rover. When we got it, we assembled it right away and tested it before we printed out some serious components. And some of those components included the 2 excavator claws designed for regolith extraction, a storage container to store the regolith in water during navigation, and 4 tire fenders to protect the rover body and tires from lunar dust and some environmental obstacles. And all of this is recorded in our databases as we walk through it. And then we have the Leo rover and the robotic arm. Once we got it at our spec office, the Leo rover prototype was assembled right away. We took the Raspberry Pi that was on board and configured it to allow it to be controlled via a user interface from a spec laptop. And similarly, we took the robotic arm from Amazon, assembled that upon delivery, and put it together with all its servo motors, and took the Raspberry Pi to modify it. And we also modified the arm and outfitted that with the 3D printed excavator claws that completed to help create the excavation subsystem. And the Raspberry Pi was configured to be controlled using a remote. Okay. And once we had everything together, all the Lunar Rover prototype components and the subsystems printed, built, and assembled, the final product was Spec Innovation's Specter, a Lunar Rover prototype here. And if you were wondering, Specter stands for Space, Prospecting, Excavator, Convoy, Transporting, and Evaluating Regolith. You got to see a little bit of it in the slide before, but there was a user interface that was created to control Specter, shown earlier, which was done by creating a repository in GitHub. See, the prototype's firmware already allows messages to be sent from user interface to the prototype's equipment and components to let command functions be performed, such as like moving forward and backward. And to access GitHub View, we have a token that is granted per team member to access GitHub via InnoSlate's GitHub View, which will display all the repositories on GitHub dashboard and allow team collaboration on the issues. And we created a GitHub issue every time we needed to record data or display messages in the user interface, which included detecting the obstacles, calculating distances, and displaying voltage output, and even our company logo. And every modification involved writing code and then publishing those updates to GitHub. And we're still staying within the same InnoSlate database. Everything is stored in one location. Okay. Then we revisit the rover route to conduct an analysis on the Lunar Rover's map travel route that we created in task 1 earlier. And so we used ANSYS's Systems Toolkit, SDK, to model the rover's travel route on the lunar surface to help calculate the time to reach the mission goal of 10,000 kilograms of water. And we made several assumptions in the model, including but not limited to how the same route is used for each process, excavation rate of 100 kilograms per hour, carrying capacity of 100 kilograms per hour, 10 excavation cycles before needing to recharge, as well as some other ones such as like 4 hours to recharge, unloading regolith will take 15 minutes, loading water takes an hour, some values there. Okay. And then as part of the analysis, InnoSlate's integration with SDK allows us to improve the fidelity of our action diagrams by exchanging data and information between the platforms during a simulation. And we created this one rover sequence scenario action diagram to co-simulate the mission scenario with SDK. This diagram represents one lunar rover excavating regolith from the surface, transporting regolith to the water extraction plant, and then ultimately delivering the water for long-term storage. In the diagram, the simulation ran until either 10,000 kilograms of water was achieved or 365 Earth days had passed. And after we created the action diagram alongside the STK model, or during, I should say, the scripts were added to the relevant action entities where the rovers referenced. And we needed to script these because the scripts communicate with the SDK software in order to initialize SDK, to create some of the global variables, to store those time to traverse values, calculate duration, velocity components, and ultimately calculate travel times between sites. And this gives us the benefit of using realistic time values to use in our action diagram simulation. So after executing the discrete event simulation in the diagram, the simulator calculated a total mission duration of 10.67 months to collect 10,000 kilograms of water relying on the previous assumptions. We also calculated a total travel distance of 3,500 kilometers that needs to be covered by the Lunar Rover to do this. And so we could see as well from the resources over time section of the simulation that this kind of mission will have the majority of the time be spent by excavation and extraction processes, of course, relying on our assumptions. And delivery time seems to take a whole lot less time than actually mining the water from the moon. Okay. And we took the results that we found in the co-simulation and then verified it by using another co-simulation with MATLAB. To do this, we use the same velocity vectors that were provided to us by SDK's software as the rover is moving along its path. But we took the velocity vectors and instead of calculating it through SDK, used a MATLAB function script to calculate the magnitudes of velocity and calculate the times from there. After running the simulation, we found largely the same results, identical results to the first co-simulation. And we used the API GET request to retrieve the velocity vectors from SDK, and yeah, showed the identical mission duration and total distance traveled values that you see on the resource final amounts chart. Okay, that moves us on to task 3, the test phase, for testing the Lunar Rover prototype. And in this one, we used InnoSlate's test center and ANSYS software throughout the testing processes. Inside the system engineering V model, we would say this takes place during the integration and test, operations test and evaluation, and transition phases. Go. We broke task 3 down using a SOW as well into several other subtasks, creating verification and validation requirements, test cases, simulating the lunar environment, testing the Specter prototype, conducting performance and environmental analyses, and incorporating InnoSlate's digital thread. And from this task, we created 2 final reports, one for task 3 and one as an overall final engineering report. And it's really good that everything's together in one space because I could review some of those final documents before they're being submitted anytime I wanted to, as well as our I'd say our sponsor to look it over. Go. So for verification testing, to start that V&V process of the Specter prototype, we created test suites in InnoSlate's test center to hold different test cases for testing the rover and each of its components. And this was intended to verify the rover's functionality by making sure that everything operates properly and as expected. Once we had the test cases drafted, they were traced back to their corresponding requirements for complete end-to-end traceability. And our test suites verified aspects of the robotic arm and the servo motors, excavator claws, and the Lunar Rover prototype. And these tests are like basic things. They included basic things such as battery runtime, payload limits, and wireless communication stability. Okay. To review the excavator design, we used ANSYS's space claim and static structural to provide further analysis of the excavation claws used on Specter, and we intended to help locate and find any potential design flaws. During the analyses, we calculated the following metrics: surface area, volume, maximum load capacity, maximum pressure tolerance, and after all these analyses, the results and the metrics were inputted into the mission and excavation scenario models to help improve their simulation fidelities. So on ANSYS Space Claim, we used a model of the excavator design claw and uploaded that to the Space Claim platform, where the CAD drawing would be analyzed more in depth. And Space Claim went ahead and calculated those measurements like the surface area and the volume, which were then inputted into a modified density equation that included estimated regolith density to help determine maximum load capacity supported per dig. And this value would ultimately be around 232 grams of regolith for the prototype, which we stored in our equation editor. Okay. And we continued the excavator design analysis with ANSYS static structural, and this platform helped us look at pressure tolerances for the excavator claw. And to do this analysis, we realized that we couldn't really assume that we would always get the maximum load capacity for each dig. So we varied the load capacities between 60 and 80% to kind of get a gauge on it. And there was a pressure equation used for each capacity to calculate those pressure tolerances during operations. So the analysis showed that there were pressure tolerances of 3.4 PA and 4.5 PA for the 16 80% capacities respectively. We used the report given by the tool to help us improve the support joints for the claw, shown in purple, and the impact areas shown in red, which gave us a better idea of how the claw will be affected during the operations. And after completing the previous analyses, we conducted more structural analyses of the excavator design this time. And this was to help determine the strength and stability of the excavator claw design under different loading conditions. Strain, stress, and deformation tests were conducted for each of the 16 80% levels in order to help us find any more design flaws that we needed to be aware of. And these would all be recorded in an InnoSlate document. And from there, it could be traced to other entities as a source document and referred to by other team members at any time. And as mentioned before, we used InnoSlate's test center to help develop test cases for the Leo rover, shown here. And we based these test cases on the manufacturer's documentation and specifications, meant to verify that the rover can meet its defined functionality according to those documents. So you'll see things like power on, power off, max speed, payload capacity, that sort of thing. Okay. And so after completing the verification of the Specter rover prototype and its subsystems, we had test plans that were created to begin the validation of Specter's functionality against the expectations and the mission requirements of the Break the Ice challenge. And these test plans included speed and travel times for navigation, regolith excavation and collection, materials containment and protection for storage, and equipment protection with dust mitigation. Okay. And as required by the challenge, we also performed performance analyses of the Lunar Rover system. And this would help validate Specter's functionality and efficiency. And some of the parameters that we calculated included total landed mass, including separate values for the rover equipment and the NASA water extraction plant, total power consumed with separate values for the rover and the NASA water extraction plant, and total water mass delivered. Okay. But due to time constraints on this presentation, I'll just go over the landed mass and the water mass analyses. And so to start, to determine the mass of the full-size Lunar rover in proportion to the Leo rover prototype, we used a ratio between the rover's carrying capacity and the rover mass itself to just kind of get in that ballpark area. And so we saw the Lunar Rover had a carrying capacity of 5 kilograms and a mass of 5.4 kilograms, and that gives us the ratio of 5 to 5.4. And we wanted the full-size rover to carry 100 kilograms ideally, so we used the ratio to kind of estimate that the full-size rover without the equipment would be around 108 kilograms. Therefore, the full-size rover to the prototype ratio will have a mass ratio of about 1 to 20, or prototype to full size would be 20 to 1. Okay. And in addition to the Lunar Rover body, as I said before, we also have other equipment and the components landed to support the mission. And this will have the negative effect of reducing the rover's total carrying capacity and increasing the total mass landed on the moon. Since the carrying capacity is reduced, this would reduce the amount of regolith or water that can be carried, increasing the cycles that would need to be carried out with increasing weight. So to kind of summarize all the results, we believe that the total mass of the full-size rover, including the supporting equipment on board, would need to be less than 160 or 186 kilograms, or around 190 kilograms roughly. We know that the mass value for the NASA water extraction plant is estimated at 700 kilograms. That was provided in the documentation. So combining that together, that makes the total mass landed on the moon would need to be around 886 or 890 kilograms. There you go. Okay, lastly, we did have environmental analyses to observe the extreme conditions that we know the rover will need to withstand while it's on the lunar surface. And we took these conditions as risks that needed to be mitigated and came up with the following. We had warm electronics box to deal with the low temperatures, the sub-zero temperatures on the moon, a wide set body frame and the rugged wheels to handle the reduced gravity environment, non-pneumatic tires to handle the vacuum of space, because you can't have a regular tire in space, and tire fenders to prevent lunar dust from entering the rover body, at least not as easily as it travels. And this is all kept in our documents view. Okay. And as the last item on our presentation, we do have the results of our work recorded on YouTube. And I'm going to play it right now, but we've also recorded many more videos and presentations on the topic, so feel free to look them up on our YouTube channel. Gonna go ahead and play. All right, and I think that kind of concludes the presentation, so I'll pass this back to Taylor.
Thank you, Andy. That was great. We would like to thank you again for joining us today. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for our next webinar, Program Management in MBSE, on Thursday, October 12th at 2 p.m. Eastern. Be sure to register whether you can make it or not to receive the slides and recording. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.